we're talking about maybe doing an alternate method of this, and the picture on the next section shows off an alternate method here. And I've stolen these pictures right from your textbook. It says, consider the problem above, again, using a different geometrical look, which without the demos, I'm not sure that this is hard to pick, that it's easy to picture. But now with some demos on it, maybe we can look at this and see what's going on here. It's this. It's this demo right here. Say there's going to be a whole bunch of shells that we're going to do all the way out. Yes? And each shell has thickness dy. A little bit of y. That's weird that it's now switched over to dy's, yes? But now, if we want to evaluate this volume using this new geometry, what we got to do is go, okay, volume equals integral a to b. Now, this shell, let's talk about the volume of this shell. It's going to have dimensions, length, width, and height. It's going to have these three different dimensions. And that's not a formal answer. I'm just sort of writing that so that I can get used to. The length is going to be this 2 pi times the radius of the shell. I'm actually going to write that just like that. Radius of the shell times the height of the shell times the width of the shell, which is dy from the picture here. It's that little shell thickness dy. And the dy really tips me off that this all better be in terms of y. That's the part that you're going to maybe find difficult. I need y's in all this now. So, 2 pi. I'm going to skip over the limits of integration there because I got to think about what the y limits are now. Shell radius. That's not too bad. The shell radius is not too bad in terms of y. It is the y value. The shell radius each time as you go along, the radius of the shells as you go along is the y value. That's hard to see in the 2D picture. This is where the visualization comes in. You got to be able to draw this picture on your page and picture these shells going along the outside here. Maybe my little demo helps to understand that as we go along here, the shapes of those shells is going to change. So the radius is just the y value. Now, the height of the shell in terms of y, that's hard. The picture's already shown it, but I want to walk through it. The height of each of these shells is going to be, well, all the way across, which is 4. They could be height 4. The first one might be pretty close to height 4. Look at it. The very first one, the very first shell has a lot of height. It might have the full height of the whole bowl. But then they start getting smaller and smaller by an amount that they left out of the picture here. I think they should have put a little x in there. That's the x value that you're doing on any particular shell. But what is x? Y equals root x. So y squared equals x. So that's where they get the 4 minus y squared from. That's hard. That's hard to pick all that stuff out of there. You need a great 2D picture and some great visualization to pull it off. In the end, though, if I get the height of the shell is 4 minus y squared, then I'm home. Yeah? Hopefully your integration skills are such that when you get to that moment, you're feeling pretty happy about the whole situation. Yeah. The whole height of the bowl of the paraboloid is 4. And as these shells go along here, they get smaller and smaller. 4 minus something. 4 minus the x value. Basically, that's the x value every time. But x equals y squared. Why did I switch over to y? What is it about the situation that told me I got to get it all in terms of y? I'm integrating in terms of y this time. The shells are going out y in the y direction. Now that makes my limits of integration different as well. Only 0 to y value 2 now. No. If you would have done the question with the slabs, with x, then you'll do the shells with y. So it'll go back and forth like that. So these particular ones, the shells are horizontal, so we're going to do the integral vertically. Picture it this way. There's the horizontal shells. I'm counting them vertically along the way there. Question? Oh, because I'm integrating with respect to y now, so the top one is now 2, not 4. Yeah? So you got two different choices. You can do with x's with y's in this question. And again, let me remind you, if you ran into this question in the homework, you'd probably, I think they got carried away in the solutions, right? They started doing everything with shells, and they even screwed up a couple, I think, trying to do them with shells. But shells isn't the end-all, be-all. I'm not trying to say that. You're going to see in the next example that shells handle ridiculous situations. Okay, so I got to finish this integral out. Volume, and really hope I get the same answer. That would prove that this method works, is that if I get the same answer. So bring the 2 pi out front. Keep the 0 to 2 in there. Multiply out what's left, 4y minus y cubed. Just double check all that stuff. The 2 pi came out front, 0 to 2. Multiply out what's left in the brackets, 4y minus y cubed. Yeah, I'm feeling pretty good. Volume equals 2 pi. Now the antiderivative is 2y squared minus a quarter y fourth. And I hope I've set this up right. Can you see that the second bracket, when I sub in 0 to the second bracket, I'm going to get zeros all the way across. So I can just leave that out. That happens a lot with integrals during volumes, is that second bracket is 0 anyways. So I get volume equals 2 pi. And when I sub in 2, I get 2 squared is 4 times 2 is 8. And then this is a 2. No, it's not a 2. It's y to the power 2 to the power of 16 divided by 4 is 4. And I get 2 pi times 4. I get 8 pi. Whew! Good. Same answer as the previous one. I've now landed the cylindrical shell method on an easy one. Yeah? Hopefully you're thinking, okay, I would never ever do this on the question that was given. There was no reason to do cylindrical shells here. It's just to show that it works. What questions do you have before we move on to the tough examples of the day? Oh, tougher. This might be one of the toughest examples we've done this year. So if you're having a little bit of trouble with it, you're like, I sort of got it, but not really. Yeah, tough stuff. It's why there's a review lesson after this to go, let's just go over all this again. Yeah? Tough stuff here. Question. The shell radius, in this picture here, I could see the shell radius was right there. And that is the y value.
Even if we were to look 2D, the full radius would be 2 because of full length.
Yeah, so there's the, and so if you want to draw on here, it's not as easy to draw on here, but there's the, in 2D, right? No, on a 2D picture. I'm drawing that thing out there so you can see that shell. And you see how that shell's radius is going to change as the y value changes. The radius is the y value. Did that help? Other questions? All right, well, let's leave that one and move on to one that I really walk through the individual steps. This is like a motivating example to say, okay, I sort of get what's going on here. Now I'm going to do one that has to be done using cylindrical shells and go through each step and just talk about each of the individual pieces that come along here. Integrating volumes using cylindrical shells, that is going after pieces of cake. We know how definite integrals can be used to calculate volumes using cross sections, using disks. Sometimes, however, a solid is created in such a way that the cross-section method is very inconvenient. For example, consider the following situation. The region enclosed by the x-axis and the parabola, here it is, f at x equals 3x minus x squared, is revolved around the line x equals negative 1. So this parabola is going to revolve around x equals negative 1, and you're going to end up with a shape that sort of looks like this. Have you ever had one of these cakes before? It's called a bundt cake, and it's got a weird shape to it, but it's perfect for this example. See the little parabola in the cake there? There it is right there. And I don't know how they're made. There must be a bundt cake container that you bake in the oven this with. But imagine instead that how we did is we took a parabola and just wrapped it around like that. That's basically what it is. It's a bundt cake. And so here, this parabola got wrapped around negative 1 and created a bundt cake. Yeah? That's the volume we're after today. It'd be nice if you could picture the bundt cake a little bit better. I should have brought one. We should have made bundt cakes. You could be snacking away on the toughest lesson of the year. You could be snacking away on a bundt cake. Brutal. All right, maybe next year. I'll tell you about it next year. That's what I'll do. You text me like, hey, we had bundt cakes this year. The graph on the right shows, okay, so verify algebraically that the parabola intersects the x-axis at 0 and 3. Okay, well, this isn't too bad to start off with. Actually, what we're finding is the limits of integration. So we're just going 0 equals 3x minus x squared. When does the parabola hit the axis? Okay, we're way back. We're just going to grab some grade 10 skills out here for a moment. I've been just hammering the advanced functions people with this yesterday. What kind of factoring? Just common factor. Be nice if they saw this lesson. I was too bad it's not on the board, so they see that I'm not just freaking out for no reason. Common factoring is really important. Therefore, x equals 0 or x equals 3. Verify that the parabola intersects the x-axis at 0 and 3. Yes, I did that. We're off to a great start. I found the limits of integration, at least, in this very tough question coming up. More time here? Next, the diagram on the right. Oh, what a great diagram. It's a beautiful picture of what's going on here. The parabola has been wrapped around the line x equals -1, creating this bundt cake. Suppose we were to use the washer cross-section method. Okay, it's awfully tempting to do washers here. Can you picture the washer? Oh, it's hard to picture the washer. Hold on, maybe I've got something.